Institute Research Committee. I am welcoming you for the Research Methodology Workshop Day 6. Today we have two presenters from the JIPMER, Professor Dr. N. Sreekumaran Nair and Dr. Harichandra Kumar. Ma'am, shall I ask a recap now itself?
Yes, sir. Yes, sir.
Nice. Now I request Swapnil to give recap about yesterday's presentation. Swapnil. She's not there, sir.
There are two people now, one more person.
Yes, sir. The other candidate, Malayali, can give a recap about yesterday's presentation.
I think no problem. I can give a recap because
Okay.
I know what was overall there. Okay,
Yes, sir.
so no issue. Shall we go ahead?
Yes, sir.
Okay. I just see. Is it okay? Slides visible?
Yes, sir.
Okay, and am I audible?
Yes, sir. Yes, sir.
Okay, good. Okay, today's session is inferential statistics. It's one, and before that, yes, definitely a recap of yesterday's. In fact, it's my first slide is the overall recap. The next slide, and not this slide. The next one, it's what so far we. I looked at the schedule. I think it's all are there. It's in the session. I looked at the schedule. Of course, it's your training started with the research questions, then AIM's objectives and hypothesis, if any. It's not always you should have a hypothesis, but aims and objectives definitely should be there in any research. And sometimes you'll have a hypothesis and sometimes you don't have a hypothesis. Okay, but anyway, all those things explained. And yesterday, when we started the statistics, biostatistics part, Dr. Hari started with it's basically he talked about an introduction to biostatistics. Then specifically he spoke about variables. Within that, he talked about the dependent variable, independent variable, outcome variable, and various types of variables in terms of binary, categorical, ordinal, all those things. I'm not going to explain all those things. It's not required. But that is an important area. That is what it's a very simple area, but sometimes people really they don't care this thing. Okay, variables we don't have to look at properly. They think when data comes, we have to analyze it. That is what people get interested, but that is absolutely a wrong approach. You have to at the beginning of your study itself, it is your duty to define your variables properly. Is it a binary variable? It is an ordinal variable or a continuous variable, categorical variable? All those definitions, it's very important and very strictly you have to do because it has got a huge impact on the analysis part of it. Okay. Not only analysis part, when we talk about the sample size or any statistics, yes, this variable definition is very, very important. Okay. And Hari yesterday spoke about it. Even the same thing you can define differently. For example, systolic blood pressure, yes, I consider it as a continuous variable. Diastolic blood pressure, I consider it as a continuous variable. But then When you talk about hypertension, basically hypertension, yes or no, hypertensive or not. But that is defined based on systolic and diastolic blood pressure. That means you measure two continuous variable, and based on that you define a third variable which is binary. So, and that is a variable, probably you use it for analysis. Glucose values you measure, okay, random glucose or it's a fasting glucose you measure. It's a more a continuous variable. But diabetic or not, you define again based on a cutoff. That means you measure a continuous and so I'm not going to the details of that. But what I wanted to reaffirm here is that yesterday, that first session, very important. That's one. And then yes, the design, actually before day 4 yesterday, I mean it's before that, it's the last week probably, you had the study design, and that's also very important when we talk statistics, and that is what my session I'll touch upon that. Then yesterday, of course, it's Hari further talked about the measurement of these variables, or you call it as data, and how to deal with the data. Then Amala took over, and she spoke about summary statistics in terms of various type of variables. If you have measurement on those variable, or you have data on those type of variable, each type of variable data, how you summarize it. Okay, some of the thing you summarize it as frequency and percentage. Some you some of the variables, it's for example continuous variable, you summarize it as mean and standard deviation. And if it is a ordinal variable, mostly summarize it as a median and interquartile range. And even if it is skewed variable, summarize it as median interquartile range. And it's Hari was speaking about its this normal distribution, and how you that mean plus or minus 2 standard deviation, mean plus or minus 3 standard deviation, all those things, how to set it. So basically, in summary, I want to tell, yesterday we spoke more about summarization of data, in the sense it's various either baseline characteristics or further even outcome variables. How do you summarize it in terms of based on different type of variable? That is what essentially we spoke yesterday. Okay. So with that preamble, we move to the next session, and that is what the statistical inference. Okay. And the statistical inference, it's today today totally we spend for statistical inference. Half of that I talk about it, and remaining half it's Hari will be speaking about it. Okay. So today overall what we do is, it's basics of inference, little bit high speed. Then estimates, yes, I talk detail about all these things. Estimate, standard error, confidence interval, those things. And for finally, basics of testing of hypothesis in terms of level of significance, power, and p-value, those concepts. And that's the place I stop. And then Hari will take over, and he's talk about the test of significance, various test of significance, like t-test, analysis of variance, all those area he's talk. Okay, so that is the probably the first 5 points. It's I talk, and the last point Hari talk, but that is a huge one. Last one is a very huge one, so he has more energy to speak that. So with that preamble, we move to the statistical inference. So what is this inference? Just look at that. Okay, you have the research question, and you have probably a research hypothesis, and then making an inference. Inference means probably answering your research question, or answering your research hypothesis. Okay, you as a researcher has full freedom to set your hypothesis, your aims, your objectives, and then based on that, design is selected, study design is selected. And based on the study design and your research objectives, you define your variables. And based on that, yes, during your research, you measure those variables. That is what you get is data. Okay. That means end of your study, you have data based on objectives. It has been measured, those numbers you have. Now that is the point. You should stop speaking and you should allow your data to speak. Okay. Once you have the data, now your perception won't matter. You should allow data to speak. And what data does, it based on the study design, and it use the probability methods to give an answer to your hypothesis or answer to your research question. And that is what precisely we call it as statistical inference. The statistical, that term is coming from the probability theory based on the concept of probability, and your design as well as your collected data, we make the inference about your research question and of course about your hypothesis. And that is what statistical inference. So the probability theory is highly utilized for this, making this inference. Okay. It is something like, I would say, your data will be passing through a funnel called a probability theory, and end of that, you get inference and answer to your research question. Okay. So you should fairly well, unbiased way, you should allow the data to go through the probability concept. And then only you can get real inference about your research question. Okay. And with that, in the inference, there are two areas, statistical inference in two areas. We will detail talk about that. One is, first is summarizing the effect measures. I am using a new word which is called effect measures. We will come more detail about it later. Not only effect measures, it's uncertainty also. Based on the data and based on probability principles, we have to do it. Okay. So that is first part, and usually we call it as estimation. Okay. And then inference has got a second part, which is hypothesis testing. And that is why at the beginning I said, it is not every research should have a hypothesis. Of course, every research should have a research question. It should have an aim. It should have an objective, but it need not be a hypothesis. For example, many of the descriptive studies, you don't have a hypothesis. In fact, those studies build up a hypothesis. It actually doesn't have a hypothesis. Okay, when you do a prevalence study, you don't have a hypothesis. You have a research question, you have an objective, but after that, you don't have a hypothesis, but that is a place you do estimation, you don't do hypothesis testing. Okay, all prevalence studies, none of the prevalence studies you do a hypothesis testing, you do an estimation only. Okay, we will see as we proceed, we see. And some of the studies you have a hypothesis, for example, a clinical trial or analytical studies like a case control cohort studies. Analytical studies, you have a hypothesis, and that is a place you use hypothesis testing, either accept or reject the hypothesis, okay, based on the data and probability theory. So it has got two parts. So the first part is estimation, effect measures and uncertainty. I spend, I think it's maybe another 15 to 20 minutes talking about effect measures and its uncertainty. And in that, there are three concepts I wanted to touch upon it. One is summary effect measures. Probably to observe was a very strange term, but you know that, and I'm very sure you many times you calculated all those things. Okay. Then of course you are familiar with the standard error and confidence interval, and we relook at it. What is that? Okay, so that is the first part of it's my talk. Okay. Now, what I thought is when I talk about effective measures and its uncertainty component is nothing but a standard error or confidence interval part of it. Okay. I thought I explain to you with an example. Okay, example is it is an estimate I am talking. So I use a prevalence study example. Suppose you are doing a prevalence study. Okay, your study is prevalence of CHD, and you know that it is a cross-sectional survey. Okay, and you planned the design. It's a cross-sectional survey, and your idea is the prevalence of CHD. That is what, and you have done. You have calculated your sample size was 8,000 individuals, and there is a mechanism to diagnose. You have a criteria to diagnose CHD and coronary heart disease. So finally, you identified 200 people out of 8,000 had the disease. So end of your survey, you have 8,000 subjects you examine and 200 individuals diagnosed as CHD. Now making an inference based on this, what do? You wanted to calculate prevalence. How do you do it? The summary measure or summary effect measure, I call it as it is a prevalence. It is nothing but 200 divided by 8,000 into 100, and what do you get? That is what that the prevalence you got it. Okay. Now you have a number. What is the prevalence? Okay. Now, one thing I wanted to tell you is, usually people have a practice when you do a survey like this, where you focus on sample size, a large sample size you focused, and CHD diagnosis you have done, calculated the prevalence, you got it, and that is all you have to report. That is the way people go ahead, which is wrong. No. This is the effect measure, and it is you are supposed to, it is mandatory, you should give the uncertainty measure or standard error of it as well as confidence interval. Because this is if somebody is doing the other way, please today make a change. When you report prevalence or when you report incidence or anything, any effect measure you report it, you have to report corresponding standard error and corresponding confidence interval. Look at it, standard error, how it is calculated. You got prevalence as 2.5%, then 100 minus 2.5, that is 97.5%. So that 2.5 is P, and then 97.5 is Q. P into Q divided by the total sample size, and overall you take it in square root of it. That is nothing but that is your standard error. Okay, that is the uncertainty measure or standard error. Okay, that is 0.175. It is a simple calculation. Using your calculator, you can calculate it, and then get the confidence interval. Yes, use this standard error, and then I use something called Z1 minus alpha or 1 minus alpha by 2. That is, yesterday Hari was demonstrating the standard normal distribution, and that Z value is coming at alpha level of significance. Alpha is mentioning of the level of significance, and what estimate you got, it is 2.5 plus or minus that is at 1 minus alpha into standard error. That will give you the confidence interval. So what you get is, suppose that alpha is 95%, that means alpha is equal to 5%, that it is equivalent to 95% confidence interval. Corresponding multiplication factor is 1.96, and 2.5 plus or minus 1.96 into that one, you get it as 2.15 to 2.84. In fact, many of the packages, including Info, will give this. You can, otherwise manually even one can calculate it. But only my point is, when you report any of the effect measure, you are supposed to report it as standard error, and most importantly, it confidence interval. Usually we report 95% confidence interval. Yes, you can report 99% confidence interval also. Okay. And what it tells is, it interpret this confidence interval tell you got your estimate as 2.5. I use the word estimate. I think it's earlier, even I spoke to many of you. This estimate means what? Basically, when you try to answer your question, your data comes from a sample. It is not the whole population you surveyed. Population could be, for example, in suppose this study being done in Puducherry, maybe 10 lakhs people in Puducherry. Out of that, a sample of 8,000 you have taken. And based on sample, you are doing all those calculations. That is why we use the name estimate. Estimate is the computation coming from the sample. That I don't have to explain further. You know that when you send a 5 ml blood sample to the biochemistry lab, what hemoglobin you get, you usually call it as hemoglobin estimate. It is not the whole blood you analyzed and you got that value. 5 ml you send it or 2 ml you send it, and based on my 2 ml blood, it's evaluated and hemoglobin is calculated, and you are telling that is my hemoglobin value. You are not telling that 2 ml blood hemoglobin value. So that estimate is work fine with my hemoglobin estimate. That is what. The same thing in research also you are doing. You are taking a sample, and based on sample you are making the calculation, but you are talking about the population. Please understand. Okay, you are talking about the population. That is why you require the standard error and confidence level. So 2.5 is the estimate you got it at, and your confidence level is 2.15 to 2.84. What it tells is, even though your sample said 2.5, it can vary. The estimate can vary between 2.15 to 2.84. That also with a 95% confidence. That means 5% chance is there, even it can go beyond that. That is what you have to understand. 5% chance is there, it can go beyond that. The estimate can go either less than 2.15 or more than 2.84. Okay, so that is what you have to understand. Interpretation of confidence level. Confidence level will tell, for example, this slide I spend a lot of time, but after this I don't spend much time, and I assume that you understand confidence level. So you have an estimate. Here the estimate is prevalence, and that prevalence, finally you calculate confidence level. What it tells is, even though you sample, this sample you got it as 2.5, it has a potential to vary between 2.15 to 2.85. That also at 95% confidence interval. That means 5% level, even it can vary beyond this limit. That is what you have to understand, interpretation of confidence interval. Okay, so I think I spend enough time with that. It's a now this is this slide is like I already explained to it. Yes, so it is an interval estimate, confidence interval and interval estimate. It talk about unknown population parameter and based on a random sample. That is very important. Okay. Now, this is a formula for it. This already you calculate. That is why first slide I spend a lot of time. So that this one, I don't know, the formula for 95% confidence interval for proportion or prevalence is P into 1 minus P, that is Q divided by sample. Then 1.96 is approximated as 2. That is how 2 is coming. Sometimes people wonder why that mean plus or minus 2 standard deviation is coming. It is nothing but 1.96 just approximated into 2. That is why that 2 is. That it is 2 is not a magic number. It is coming from that standard normal distribution. Okay. So this is the formula, and this yesterday very well Hari explained about the normal distribution, but your sample statistics again it follows normal distribution, and that's based on that. Yes, you get that limit. So usually we take 95%, and some people, if your mean plus or minus standard deviation or proportion plus or minus 3 standard deviation if you are taking, that is equivalent to 99.7%. Okay, so that is, and then earlier you calculated for proportion, confidence interval. Similarly, arithmetic mean you can calculate confidence interval. You know that standard deviation divided by square root of n, it is usually called standard error of mean, SEM. Even many journal article, you must have seen a column telling it as SEM, standard error of mean. So standard error, it's any of the population, any of the sample estimate you calculate for everything, you can calculate corresponding standard error, and you must calculate corresponding standard error. So now with that, I spoke about proportion, I spoke about mean, arithmetic mean. And please understand, anything you calculate, you estimate from your sample. It could be prevalence, it could be incidence, it could be odds ratio, it could be relative risk, it could be hazard ratio, it could be correlation coefficient, it could be regression coefficient. Any of these things you estimate from the sample, usually we call it as effect measure. Okay, all these things together come under one umbrella. It is called the effect measure. And any one of these, when you estimate, you calculate from your sample, it is a must. You should calculate a standard error of it. That means standard error of prevalence, standard error of incidence, standard error of odds ratio, standard error of relative risk, standard error of hazard ratio, standard error of correlation coefficient, standard error of regression coefficient. All you should report. Yes. In fact, you use SPSS or any package, it automatically calculate, but many times we ignore those. We report only odds ratio. No, you have to report corresponding standard error as well as confidence interval. We report only correlation coefficient. That is again wrong. Correlation coefficient, it's a standard error and it's confidence interval. If you report confidence interval, probably you can avoid a standard error, because in confidence interval already incorporated standard error. So you can avoid standard error. So that is a pathway. You calculate the estimate, you calculate the standard error, then proceed towards the confidence interval. And that's the way it is done. Okay. So some of these effective measures, I have one on slide to demonstrate that. Just look at it. Suppose you are doing a case control study. Okay. You already got enough explanation about case control study, so I don't want to talk more about it. But however, basically the fundamental point in a case control study is you recruit cases. That means you have a sample of cases, you have a sample of controls. Then the cases, you look back their exposure, what proportion is exposed, and controls also you look at what proportion is exposed. That is how exposure rate you calculate it. Okay, I have an example. With this preamble, you look at this example. Okay, case control study, association with childhood obesity and diabetic. Okay, so basically childhood obesity is a risk factor for diabetic. When the people become adult, they become diabetic. Childhood obesity, obesity at childhood is a risk factor or not. Okay, and you decided to do a case control study. That means your cases are these columns. Diabetic, yes, 300 diabetics, it's a cases you recruited. 600 non-diabetic controls you recruited, and then obesity is the exposure you looked at it. 125 people, out of 300 diabetic, 125 had this exposure, that is 41%. Okay, out of 300, 41% had the exposure. Then you look at the controls. Out of 600, 16%, 100 had yes exposure. Okay, so there is a high proportion here exposure, with relatively low proportion here exposure. So then the ratio of 2 exposure, and that is how you get something called an odds ratio. Okay, so based on this exposure rate, finally you can calculate odds ratio. Of course, if you do AD by BC, that is what you do it, but ultimately you are getting 3.57. Usually we are fond of reporting 3.57 odds ratio. But what I am suggesting is please report this interval estimate also. Okay, this is based on standard error, and this odds ratio is the effect measure or estimate, and the interval of that 2.61 to 4.89 is the 95% confidence interval of odds ratio. So I am insisting you to report this. The message interpretation of this is, even though this sample you got odds ratio of 3.57, and you know how to interpret odds ratio. 3.57 means it's odds ratio if it is much more than 1, you call it as it is significant, and this is a risk factor. Okay, odds ratio interpretation is when it is more than 1, it is considered as a risk factor, and if it is less than 1, it is considered as a protective factor. If it is around 1, it is called a no association. So odds ratio is a measure of association. Okay, now so that is an interpretation of odds ratio. And how I interpret a confidence interval is, yes, 3.57 is the odds ratio, but this odds ratio can oscillate between 2.61 to 4.89. Okay, that means this can even oscillate within this interval and with a 95% confidence interval. That means 95% surety or reliability, you can tell the odds ratio ranges. If repeated studies, even if you do, odds ratio likely to range between 2.61 and 4.89. Okay, that means the other side is even 5% chance is probability is there. Chance means probability is there. Even it can go beyond 4.89 or it can come less than 2.61. So that chance is also there. You are not telling 100% sure it is within this interval. Okay, so 5% chance is there, even it can go below 1. So that means someone else can come out with a study telling that childhood obesity and its diabetes, they are not associated. You don't have to get too much surprised about this. However, that study is such type of results is very unlikely, or it has a probability less than 0.05. That is what it has got, a probability less than 0.05. So I talked about interpretation of odds ratio and interpretation of 95% confidence interval. Okay. Now, so one study, it's again, I spend a lot of time, but then remaining studies, I don't spend much time. I finish. For example, a cohort study, you take it. It is the other way you look at it. You start with the exposure, and then people developed the disease or not. That is the way you look at it. And so since the study approach is like that, you had enough class on that. You had a full session on cohort studies and study design. So I don't want to spend much time. But however, when I look at this table, there is a way I look at it. Earlier, I looked at this way, column wise, but now since it's a study design is a cohort one, I look at this way. That is why I took the same example, childhood obesity and diabetes. But here, I started recruitment based on the obesity. So I recruited 2,000 people. They had the exposure, and then followed them up. And over a period of time, 750 out of 2,000 developed diabetes. So 37% developed the diabetes. That is the incidence of diabetes. Okay. So cohort study, you get incidence. Then 4,000 people without obesity, I recruited, followed them up, and in adulthood, 500 developed That means 12.5% developed diabetes. Okay, so 37 versus 12.5, and that is the and once you have this type of incidence, yes, you can calculate incidence among exposed and corresponding confidence level. I don't want to explain anything about confidence level because I spend enough time on it. Incidence among unexposed confidence level, and the ratio of two incidents is relative risk and 95% confidence level of relative risk. Okay, and you know how to interpret the relative risk as well as confidence level. Similar to odds ratio, the relative risk also interpreted, okay, and 95% confidence interval also interpreted. So bottom line is, please go beyond effect estimate. Go to the confidence interval, that means the standard error, and then confidence interval, and report effect estimate always with a confidence interval, so that what is the level of uncertainty you are clearly talking based on your data, and you are allowing your data to speak. Okay, similar to, suppose you are doing an intervention study, RCT, effect of structured physical activity, again the same issue. Okay, RCT, effect of structured physical activity, and then it's on glucose control. Okay, here what you looked at it is, there is I mean, people are pre-diabetic probably, and intervention is structured physical activity it is given. You have given one group of structured physical activity, and another group, control group, they did not get any structured physical activity, usual care they got. And so 625 individual randomized to physical activity group, 625 individual in the control group, and the physical activity group 475 could control their glucose levels. That means around 76% could control their glucose level, whereas in the control group only 250, that means 40% only to control their glucose level. Okay, so you find more proportion number of people could control their glucose level because of probably structured physical activity. So again, it is a RCT, but its analysis is more or like a cohort study. It happens, okay, and so that is why relative risk you can calculate. You got the relative risk as 1.95 and confidence interval, okay, and you know how to interpret it, okay. So through all this, what I said is, now a case control study I took, a cohort study I took, the RCT analyzed, or a prevalence cross-sectional study. And most of the time, yes, you got an answer to your question. For you had a question, there is an association or not, yes, you got an answer. Okay, that means your analysis is over here. That is what I wanted to tell. With the effective measure and corresponding confidence interval and confidence interval calculation, you realized that a standard error and a normal distribution coming. That is what I said. The data has been moved through a filter called probability concept, and through that you get effective measures and confidence level, and your inference is done. This is what the part of inference estimation I would like to talk. Okay, so this is what the part of estimation I said, and I can keep on talking hours about this estimation because hazard ratio is there. So many things you estimate from your sample. Only bottom line message I wanted to tell is, whenever the outcome measure you calculate an estimate, either prevalence, incidence, odds ratio, relative risk, hazard ratio, or mean, arithmetic mean, or median, or anything you do it, please report corresponding standard error and confidence interval. Then only your inference part is complete. Never avoid reporting that confidence interval. And mostly we report 95% confidence interval. Even you can report 99% confidence interval. Okay. So that is the first part I would like to tell. I can share these slides, no issue. And this is a summary of what so far I talked. A continuous variable in terms of mean standard error confidence interval with a skewed distribution in terms of geometric mean, geometric deviation. Or yesterday, Amla must have talked about the median and interquartile range. Or that is what a ordinal variable usually in terms of median and interquartile range. Categorical variable frequency, relative risk, odds ratio, risk difference, always report confidence interval. So that is first part of my presentation. Okay, estimation part. Okay. Now, I think all are awake, I think. Okay, because that is a online presentation, always that is a problem. I don't know how many people are sleeping. I'm definite, I am 100% sure somebody will be sleeping. But the only thing is, I don't know the number, how many are sleeping. Okay. So anybody want to respond to tell me that it's I am not sleeping?
Then we can find out the confidence interval for that one also, sir.
Yeah, you can
Not
find out
sleeping,
the
sir.
proportion of sleeping and confidence interval of that. Okay, you can, yes, you can calculate that. What proportion is, it's a rare event or it's a very, regular event, you can look at it. Because it's a very, very danger. We are talking statistics and we are talking afternoon. The both things are there. Okay. Now, before I hand over to Hari, one more concept I would like to speak. Okay, that is the second part of inference. In fact,
Sir,
yes,
in
yes,
between,
yes.
someone wants to ask something, sir. Someone's voice we heard, sir.
Okay, anybody want to ask anything or responded to my question?
If they have question, they can type on the chat box.
Okay. Hari, just look at chat box. Anybody put anything?
Nothing, sir. Nothing. So far, nothing, sir.
Okay. So we move to the next part.
Sir.
Yes.
One question has come, sir. Shall I read it, sir?
Yeah, please.
When we represent confidence interval in results of the study, does the representation depends on the precision with which we calculated sample size? For example, if we calculate sample size using a precision of 10%, should we use 90% confidence interval instead of 95% confidence interval?
No. I think it's a sample size. Tomorrow we are talking. That time we talk it, but at least I wanted to tell that is it. The precision is different. This yes, the confidence interval when we talk about 95%, it is that alpha level of significance. That is the one we are talking about it. Okay. So that question, Hari, we will answer tomorrow. Tomorrow we are talking about sample size,
Yes.
Yeah, we answer that one. Okay. Now, but it is good question. It's a one thought about it. That's a good question. Okay. Tomorrow we'll repeat that question. Now, move to the second part of inference. That is what I said when you have a hypothesis. It is not always you have to have a hypothesis. You can have a research without a hypothesis, but some, especially analytical studies, you have a hypothesis. Okay, and it has got two parts: testing of hypothesis and test of significance. I will talk more about. I spend next remaining part of my time for testing of hypothesis, and test of significance Hari will be taking over. Okay, what is testing of hypothesis? It is a statistical procedure. So when I tell the name, the statistical procedure, that means it is a using probability rules by which one conclude whether accept or reject the stated hypothesis. That means when you start your study, after aims, objectives, analytical studies or RCTs like that, it's you state a hypothesis. Usually you state a research hypothesis, then from that we build up a null and alternate hypothesis. Okay, so those are the things at the beginning itself you can make it. Then you generate data, and based on the data and the statistical procedure, And there is a level of uncertainty or level of certainty. That means it could be a 5% level of certainty, or 5% level of uncertainty, or 95% level of certainty, whatever you call. That means you use probability principle, you use data, and you use some level of certainty, and then you give an answer to the hypothesis in terms of accept or reject the hypothesis, or reject or not reject the hypothesis. Okay, so you give an answer to that, and that the overall that conceptual framework is called as testing of hypothesis. Okay, overall that conceptual framework, it is conceptual framework, and it will sit with you as a conceptual framework. Okay, and then based on a type of data or type of variable, type of data, behavior of the data, various procedures you follow. Okay, overall procedure continue, overall basic concept continue to be same what earlier I talked, and I give a little more explanation later part. But then based on what type of data you use, that very beautifully Hari is going to explain to you. You use various test of significance to answer the hypothesis or accept or reject the hypothesis. Those are called test of significance. Basically, for example, you heard about chi-square test, you heard about parametric test, you heard about student t-test, analysis of variance, man-Whitney test, Wilcoxon test, like that. So many tests of significance you heard about it, and he will be going to explain that. Okay, so that depends on the data it is decided. So that is a test of significance. So inference, when it comes to inference on hypothesis, there are two parts. One is testing of hypothesis overall principles, under which alpha, power, and p-value. Basically, these three concepts comes, and type 1 and type 2 error comes. And then depending on the type of data, type of variables, various type of various different category of test you use it, which are called the test of significance. Okay. Now, to the first part to explain, that means testing of hypothesis, or precisely level of significance, power, and p-value. To explain those three concepts, I take a set of data which we have used earlier, that RCT data. Basic question here is structured physical activity beneficial in glucose control or not? And you got already you got an odds ratio as, or a relative risk as, I think it's 1.75 or something, confidence interval more than 1, which clearly tells yes, structured physical activity is really beneficial. Okay. Now, suppose you wanted to move that one step further. Since it is an analytical study, it is a randomized controlled trial, you wanted to do a test of significance, and passionately you wanted to attach a p-value for it. That is very important. You wanted to attach a, because we are fascinated by p-values. Okay, you wanted to attach a p-value, and that is a place we move towards testing of hypothesis. Okay, so the question is a structured physical activity is beneficial in glucose control? And probably when you research proposal, when you write research hypothesis, you may write it as physical activity is beneficial for glucose control. That is usually a research hypothesis. When we use the word hypothesis, basically hypothesis is a statement. You can make any statement. Okay, that statement is a hypothesis. But in science, when we make a hypothesis, when we make a statement, it is our primary duty is with the data, we have to either prove that hypothesis or disprove that, or we have to finally, based on data, we have to speak, yes, accept that hypothesis or reject that hypothesis. Otherwise, science won't be complete. Okay. Otherwise, it will become just politics, making a statement, oh, physical activity is beneficial, and go away. that is not right. You have to really demonstrate with the data, or you should allow data to demonstrate that this statement is right. And now, next 5 to 10 minutes, what I'm going to talk is how a statistician or probability concept proceed with this hypothesis. You give this data to me and you give this question to me, and how I make my framework to give an answer to this question. Okay. What I do is I build up few things. One is I build up a null hypothesis. As a researcher, you need not have to build up, but as a statistician, I have no choice. I have to build up this hypothesis. Okay. So my null hypothesis is usually we are, statisticians are usually sadists. So we are always look at it, it is not working. I know that you are so passionate, you developed the physical activity program and you always feel it is working. But as a sadist, I am feeling it is not working. So I assume that my null hypothesis is structured physical activity is not beneficial. But what guarantee I am giving is I don't make such a statement and run away. I make such a statement and then I use your data and I allow your data using probability principle to speak, accept my statement or reject my statement. And data tell accept my statement, then you also have to accept my statement. Okay. But data tells reject my statement, then you can have your statement correct. Okay. So that is what the statistics are. So I'm allowing data to do that business. It's not I am doing that business. Okay. So null hypothesis is physical activity is not beneficial. And in case that is rejected, the alternate hypothesis is structured physical activity is beneficial. So I'm not running away with my null hypothesis alone. I'm putting a alternate hypothesis also in place. Now, with this, see, next one more point I wanted to tell is I already stated at the beginning, whatever we talk based on a sample. You have a population, and from the population you take 1 or 2 samples, and based on that you are talking. So please accept that there is a level of uncertainty. There is a level of uncertainty, and there could be, even if I make a final decision, there could be a chance of mistake in that decision. That as a policy maker, as a, the administrator, every day you people are making decisions, but there is a small level, it could be a very small level of uncertainty and error could be in that decision. Okay. Maybe after 1 month you may feel, yes, it's a decision probably wrong. That is what we are feeling now. Sometimes at least a fraction of population or administrator thinking that, oh, we went wrong in management of COVID too. Okay. When, wave 1 we managed well, wave 2 came, oh, we decided many decisions we made, but something went wrong. Now we are feeling it. I mean, at least a fraction of population feeling it. What I'm telling is always accept that whenever we make a decision, there could be a small chance probability of error or probability of my decision could be wrong. So as a best person, decision maker, what I could tell is at least how much would be the probability. If I can tell how much would be the probability, that is a great thing. Okay. And that is what through next table, I am going to demonstrate you. Look at this table. Just 1 minute, you look at this table. That time I have some water. Look at it. This is a simple 2 by 2 table. Top, you look at it. process of hypothesis testing. In that, it's inside that table. If you look at possible conditions of null hypothesis. Okay. What is null hypothesis? Structured physical activities not effective. Okay. Really, it could be true or it could be false. These are the two possible conditions. Okay. So null hypothesis, that is basically, I said it is my assumption. So it could be true, it could be false. Now, you look at the left side of that table, possible actions on null hypothesis. Who is taking the action? Data is taking the action. It is not I am taking the action or you are taking the action. You allow data to take action. What data? Action on what? Null hypothesis. What are the possible actions? Data tell accept the null hypothesis or data tell reject the null hypothesis. So that means the null hypothesis has got possible two states, true or false, and data can either accept or reject the null hypothesis. That is the way I made 2 by 2 table, 2 rows and 2 columns. Now, look at it. Possible condition, yes, null hypothesis was true, and data also told you to accept that null hypothesis. That means the first corner, it is correct action. It is just like your sensitivity specificity table. Okay, it is nothing other than your sensitivity specificity table. It is really true. Null hypothesis is true, and your data also told you to accept the null hypothesis. It is a correct decision. And then the specificity place, if you look at it, the null hypothesis is false, and data asked you to reject the null hypothesis also. Again, it's a correct decision. So that diagonal entries are correct decision. Sensitivity entry and specificity entry correct decision. Okay.
Malayali. Correct decision.
You look at the other two side.
Malayali.
You look at the down left corner. It is written it as type 1 error. What is it? Null hypothesis, in reality, it is true, but data told you to reject that null hypothesis. Once data tell you have to follow it. Now data is your boss. End of your study, your boss is data. So data tells you have to follow it. The null hypothesis is true, but data said reject the null hypothesis. That means what data said? Data said, yes, reject the null hypothesis. Anything? I don't know, some music is coming. Any issue? Any problem?
We need to unmute people, I think.
Yeah.
You can continue, sir.
Sarah, am I audible? Any problem?
No, I think some people have kept their mic on.
Okay, sir. Yeah. So just to look at it, type 1 error. That is a mistake. Probably it is a mistake. It is an error. Sometimes it's unavoidable. Null hypothesis is true, but data tells reject the null hypothesis. That means intervention is really not effective, but data tells reject that and tell the people intervention is effective. For example, a treatment, it is not effective for a drug is not effective for COVID, but based on the data we tell it is effective. All of a sudden we promote that drug and people start using that drug. That is a type 1 error. That means you push a drug into the market which is not working really. Truthfully, it is not working, but based on your data, you push that into a market. Definitely pharma will be very happy with that. Okay. Now move to the type 2 error. What it is? Their null hypothesis is false. That means there is a scope with this intervention. However, your data set accept the null hypothesis. That means an effective intervention, really truthfully this intervention is effective, but the data tells please don't go ahead with that. Okay. So you are denying an effective intervention. So this is called type 2 error. These are two types of errors likely to happen. Likely to happen. I am not telling always it happens. Likely to happen. And what is our role? Our role is to identify these errors and minimize these as possible. This is the place what we do is we pass through these errors through the filter of probability. Through the filter of probability, we pass through these errors and we minimize it. That is what this probability of type 1 error. That is what I said, filter of probability. That is nothing but alpha, level of significance. So somebody asked about alpha. So when we talk about alpha, we are really trying our best to control type 1 error. That is the bottom line you have to understand. When you tell alpha is equal to 5%, you are controlling type 1 error below 5%. When you tell alpha is equal to 1%, you are controlling the type 1 error below 1%. You know that what is type 1 error now very well. Okay, so when you use level of significance or alpha, basically you are giving a warning or you are giving a guarantee to control. Yes, I controlled my type 1 error this much level. Okay, the probability of type 1 error is less than 0.05. Okay, now probability of type 1 error is usually called beta error, and 1 minus beta usually called the power. So many times tomorrow we use the power, and you must have used many times when power and 80% power or 90% power, and that is talking about type 2 error. Okay, so 90% power means you have a type 2 error controlled very much. 95% power means you have controlled type 2 error too much. Okay, that means you need probably a large sample size. Tomorrow we talk about that. So today I am talking about alpha and beta. Precisely, these are the control measures of type 2 and 1 error and type 2 error in terms of probability. That is all in this slide I wanted to. So this slide, the main points. Type 1 error, you have to, as a researcher, should understand the consequence of it. Type 2 error, you have to understand. And the probability alpha, beta, that's all you have to understand. And now I move to the next slide. The same issue with a 5% level of significance or at say 80% beta, all those things. I did the analysis. Probably I have done a chi-square test. Hari will be talking later. And when you run a chi-square test or a t-test or something, you get a third value which is called a p-value. We spoke about alpha. We spoke about beta. And then when you run a test of significance with your data, you get something. That program will give something called a p-value. And if you look at your research proposal, you find there is a statement, if my p-value is less than alpha, less than fixed alpha, we call it as significant. Okay, that means it's a p-value less than that, then that type 1 error probability you controlled very clearly, and then whatever the data tells, you can believe it at that level of significance. Okay, now what is this interpretation of p-value? Just I move to the next slide. Just take 1 minute and read it. Just read 1 minute. What is this p-value? And somebody can unmute and based on previous table interpret it, or you can write it down. This one probability that the difference at least as large as those observed found in the observed data would have occurred by chance. Okay. This statement now it is I know that it's a very logical statement. Now I go back to previous slide. Can somebody unmute and tell this? What is interpretation here based on that statement? Anybody is courageous enough? Anyway, you are not sitting in the class, so no problem. Nobody is seeing you. Who are you? You can tell. Nobody want to venture? Okay. What it is, look at here. Here it is the comparison is 76% versus 40%. So the difference is almost 36%. So structured intervention group performed 36% better than that of the control group. Now the question is, this 36%, is it just by chance or not? Okay, this 36% is just by chance or not? And what the p-value tells is, this 36% happened by chance has a probability of 0.0001. This much difference happened by chance is having a very, very, very small probability. That means this much difference is not happened by chance. Really, your intervention worked. I think is it clear, that point? Your intervention worked because this much difference happened by chance, having a very, very, very small probability. I'm not telling there is no probability. Yes, there is a rare to rare event. Yes, it could be by chance, but most often it is not by chance. There may be a one rare sample, one rare study. Yes, 36% difference could have been by chance. But most of the studies will prove that it is not by chance. Intervention really happened, really worked. So that is the interpretation of p-value. I think it's within that 2 minutes. Some extent I was able to make it. I don't know you got it or not. So basically alpha, beta, and p-value, these are the basic parameters really work with the testing of hypothesis. These three things you have to know very clearly. In fact, 5 things. You should know type 1 error, you should know type 2 error, you should know alpha, you should know beta, you should know p-value. All these 5 things you should know, not as a statistician, as a researcher you should know. If you don't know, really I think a statistician will do a high-handedness with you. Okay, you won't be able to really defend yourself in front of statistician. Whatever they tell, you have to take it that way only. Okay, then it will be in a danger zone. So type 1 error, type 2 error, alpha, beta, and p-value you must know. Okay. Then probably, so that is the probability, and here you got a probability of 0.00001. Okay. Now, why I put this other statement, low p-value, high p-value, saying many times we find even paper, the dissertation, all those things, it is very common, but paper we find highly significant. There is nothing like highly significant. Okay. Now, once you know what is the meaning of p-value, then you appreciate there is nothing like a highly significant. For example, 0.0001, somebody would have written it as highly significant. I don't understand why it is highly significant. Okay. Then somebody may write highly significant. I don't know. This is the playing with the words. Okay. So, but that actually calculate the probability. It is a very, very small probability for the type 1 error. Okay, rejecting the true null hypothesis, very, very small probability. So that is the way it is called. Okay, so don't use the terminology like highly significant or like that, all those things. It's a whatever. Yes, if you want, you can report that p-value. Otherwise, you can report at a 5% level of significance. It's found to be significant. So then the null hypothesis is rejected, and hence intervention is effective. That is a statement you make it. Okay, at a 5% level, it is rejected. So null hypothesis is rejected. Hence, we conclude that intervention is effective. Suppose you would have got the p-value as 0.1 or 0.15. Then you tell at a 5% level, yes, we accept the null hypothesis. Hence, the intervention is not effective. And stop it there. And then just allow the reader to take it whichever way it wanted. For example, you call it as a significant, but your p-value is 0.04. Okay, or you call it as not significant, your p-value is 0.06. Sometimes the reader of your paper interpret differently. For example, a vaccine trial like a COVID trial, probably a p-value 0.06, even we go for that vaccine. But a simple common cold, even a new intervention is coming, and that intervention is very costly. It's you have to pay 10,000 rupees for a dose, and common cold, and p-value 0.04. We decide, no, 1 week I can afford to have that cold, but I don't want to spend 10,000 rupees. Okay, so this is what the interpretation. So you don't work too much with the 0.05, simply report that and stop it there. So that is what the significance. Okay, so that is what, again, that table. And now I think it's you got some additional clarity on that. What is this p-value? And then so that is the basic fundamental basics of testing of hypothesis. Then under that umbrella, there are something called a parametric test, a non-parametric test, various tests of significance, all those things. That is what Hari is going to talk about that. Okay, so the next session, he will be more elaborate talking about that. I think, yes, overall made my point. In summary, when we talk about statistical inference, it has got two parts. One is estimation, another is hypothesis testing, and most of the descriptive study end up with estimation, where you estimate with the standard error and confidence level, you report it, and then testing of hypothesis when it comes, yes, their alpha, p-value, beta, all of the other type 1 error, type 2 error, all those concepts will come. Okay, and then further test of significance, all those things will come. Hari will be talking about that. I think I stop here unless a question, some question is there now or later. I don't know. I leave it to the organizers now.
Yeah, if there is a one or two questions you can take.
Yes, sir. I think around 3-4 minutes I have, so I can take 1 or 2 questions, no issue. If somebody want to ask.
If no question is there, I will ask you. Most of the studies, 80% power should be okay, or we should keep power higher. So
I think the 80% power is very comfortable, sir. 80%, most of the studies, 80% power is very comfortable, no problem. As power you increases, your power definitely should not be less than 80. As power further increases, in the sample size, it increases. Okay. And it considerably increases. It is not proportionately increases, it considerably increases as power increases. So 80% is quite enough. And some studies, it's you wanted to be too, you wanted to be too more rigid, then you can go to 90% power. But then you have to have enough money and resources to spend for it. That is also another issue with that. Okay. Otherwise, 80% is quite enough. But anyway, nobody will go for 95% power, all those things. It's because it's too much. Yes. Any other questions, sir? Otherwise, I thank you very much. Thank you very much, sir. Thank you very much, the institution, everybody, that's for the opportunity.
Yes, sir. Thank you very much, sir.
Okay.
Your clear explained presentation about inferential statistics. Sir,